Let's explore now the data storage and data management tools and techniques and how these affect our processes and decision making in data science and big data. Local storage includes traditional hard drives and on premise servers. While offering control and data sovereignty, these options often struggle with scale and redundancy. Cloud solutions like AWS, Azure, or Google Cloud offer elasticity, allowing systems to scale based on demand. They also facilitate distributed access and built-in backup systems. Hybrid storage models combine these approaches, providing flexibility while addressing privacy or latency concerns. Choosing the right solution involves evaluating factors like data volume, security requirements, budget, and expected query load. As data becomes a strategic asset, storage architecture becomes a critical decision for long-term success. What methods qualify as big data storage methods? Magnetic disks, optical storage, solid-state drives (SSDs), and network-attached storage (NASs). Each medium offers different trade-offs in terms of speed, cost, and durability. Cloud storage providers like AWS S3 or Google Cloud Storage take these physical considerations to scale, offering infrastructure as a service. You may have heard the term relational database. Besides the classical relational databases, we will explore NoSQL and graph databases. Relational databases like MySQL or PostgreSQL use structured schemas and are ideal for transactions and reporting. NoSQL databases such as MongoDB and Cassandra support flexible schemas and are better suited for rapidly changing, high-volume data. Graph databases like Neo4j store relationships as first-class entities, making them ideal for social networks and recommendation engines. Relational databases are foundational to structured data storage. They can be visualized as Excel spreadsheets with tables, rows, columns, and primary keys. Relational databases enforce strict schemas, making them ideal for applications requiring data integrity, like banking or inventory systems. They are also efficient for querying large amounts of data using join operations and indexing. However, they are less flexible for handling semi-structured or unstructured data, and their vertical scaling limits them in big data scenarios. Despite newer technologies, relational databases remain a cornerstone in many enterprise data architectures, offering consistency, reliability, and transactional support. NoSQL databases emerged to address limitations in relational databases, especially when dealing with high-volume, variable, or unstructured data. NoSQL stands for not only SQL and includes document, key-value, columnar, and graph-based models. These databases prioritize flexibility and scalability, making them ideal for real-time applications, social media, and big data platforms. Unlike relational databases, they often use dynamic schemas, enabling agile data modeling. While they offer performance and scalability, NoSQL systems may sacrifice data consistency, depending on the architecture. Graph databases are designed to represent and query complex relationships in data. Instead of storing data in tables, they use nodes, edges, and properties to form a graph structure. This allows for efficient traversal and querying of interconnected data, making graph databases ideal for applications such as social networks, fraud detection, and recommendation engines. Data warehouses are centralized repositories that store integrated data from various sources. They are optimized for analytical queries and reporting rather than real-time operations. In a data warehouse, data is typically structured, cleaned, and transformed to support business intelligence activities like dashboards, KPI tracking, and historical trend analysis. They support OLAP, online analytical processing, which enables users to perform complex queries with high performance. Tools like Snowflake, Redshift, and Azure Synapse are widely used for enterprise-level analytics. Data lakes represent a more flexible, scalable storage option compared to data warehouses. They can ingest massive volumes of structured, semi-structured, and unstructured data in its raw form. Data lakes are often built on cloud platforms and use distributed file systems like Hadoop or AWS S3. Unlike data warehouses, data lakes don't require predefined schemas, allowing analysts and scientists to explore data without constraints. However, this flexibility can lead to data swamps if not managed properly, making metadata management and governance critical. Data lakehouses are a relatively new concept that merge the structured querying capabilities of data warehouses with the scalability and flexibility of data lakes. They aim to eliminate the data duplication and operational complexity of maintaining both systems. Technologies like Delta Lake and Apache Iceberg make it possible to run high-performance analytics directly on cloud object storage. This unified architecture supports batch and streaming data, enabling machine learning and BI from the same source. Data lakehouses are especially attractive for modern data platforms that demand both agility and governance. As a data scientist, understanding this architecture will help you design scalable, cost-effective systems that support both operational and analytical needs. Data mesh is a decentralized data architecture that treats data as a product and assigns responsibility for data ownership to domain teams. This model moves away from centralized data teams and instead distributes data engineering capabilities across the organization. Each domain team manages their own data pipelines, quality checks, and metadata. A core principle of data mesh is federated governance, ensuring standardization and compliance while allowing flexibility. The goal is to overcome bottlenecks in traditional centralized architectures and support agile, scalable data operations. Without reliable storage, consistent schemas, metadata, access controls, and lifecycle governance, even the best models fail to produce trustworthy results. Data management underpins every step of the data science workflow, from acquisition to model deployment. It ensures that data is discoverable, accessible, interpretable, and reusable, key attributes of the FAIR data principles. In your future work, robust data management practices will be critical not just for compliance and auditability, but for innovation, reproducibility, and value creation from data assets. Ensuring validity and reliability is a cornerstone of good research, and it applies equally in data science. Validity ensures that your methods measure what they are intended to, while reliability ensures consistency over time or across samples. For example, a predictive model that performs well on training data but poorly on unseen data lacks external validity. Pre-processing, sampling methods, and model evaluation strategies all play roles in these aspects. Maintaining high standards of validity and reliability enhances the credibility of your findings and the decisions based on them, especially in high-stakes or sensitive applications. Data governance refers to the policies, standards, and procedures that ensure data is accurate, consistent, secure, and used ethically. Governance involves defining roles and responsibilities, enforcing access controls, and maintaining audit trails. It is particularly important in regulated industries where compliance with laws such as GDPR, HIPAA, or CCPA is required. For data scientists, understanding governance is crucial, not only for meeting legal standards, but also for building models that reflect ethical, inclusive, and reproducible practices.